So we talked last time about these various components that we needed to build a processor. And we talked about buses, just ways of routing signals around multiplexers so that we could switch where signals go. We're going to be employing these heavily today. The arithmetic logic unit, which is the thing that actually does the computations. A good way of thinking of it is that it is a programmable function where it takes two arguments and a control argument that says what to do to those two arguments, and it returns a result. So it's a pretty easy way of thinking about it, and they're very easy to build in logic as well, so they're very powerful. And then we also need addressable memory, which actually allows us to store values. And remember that since our instructions are so simple, we typically had to take our program that we wanted to implement, decompose it into a series of operations the processor is actually capable of performing, and those operations communicate through memory location. So this is why we need some kind of addressable memory for this kind of simple processor. And so we went through that process. This was the outline. We're going to be seeing this over and over again, so we don't need to spend too much time on it. But we had to figure out what are our inputs to our computation, what's the output, where are we going to store them, and then we had to figure out if we need to store constants or intermediate values. We need to assign locations for those as well. We decomposed our computation. That was very easy. It was very obvious with our previous computation. And then we translated that into machine code instructions, which was a series of zeros and ones that would control our assembly. And that's one of the things that I love about this aspect of CS24 and looking at these systems is that we look at the bits in an instruction and we don't really make a connection in our heads as programmers that those bits actually control various circuits on the processor, but that's exactly what's happening under the hood. You set a bit here and it activates this thing, or you set a bit here and it activates some other component. Then we wanted to do multiplication, and we have two strikes against us. One is that we don't have a multiply opcode because our ALU is very simple. It only does simple arithmetic. And we also don't have any loops. So we can't implement this multiplication algorithm in either, because of both of these reasons. So what we're going to do is change our processor. We are going to add the ability to branch, or jump, if you will. And it will be a conditional jump. Basically, if the argument A is 0, we will change the program counter to be whatever the address is encoded in the instruction. And if A is non-zero, we'll ignore it. We'll go ahead and just go on to the next instruction. And that turns out to be all we need to do to implement our multiply operation. So this is our change in our logic. You can see that we're kind of bolting things on. This is not the way we would really like to design a processor. Hardware design is the same as software design in that you'd like to have a nice, elegant, unified abstraction. But here we're just sort of bolting things on as we discover abstractions we need. So we have our opcode feeding down to the branch logic as well as to the ALU. And we have A feeding in, or I should say the address for A from the instruction memory down. And you can see the output of A now goes to the branch logic as well as to the ALU also. And then we have this little multiplexer up at the program counter, which will take the signal from the branch logic, and based on what the branch logic decides, we will either feed program counter +1 into the program counter, or we will feed the address from the instruction memory into the program counter. So this is the simple description of the logic. If the opcode is BRZ, our branch logic will activate, and it will look at it will look at the output of the A value, and if the A value is 0, it will update the program counter with the branch address in the instruction as opposed to just incrementing the program counter. Okay? Does that make sense to everyone? Now what's unusual about this is that you'll see that we feed the opcode to both the branch logic and the ALU. And we feed A to both the branch logic and the ALU. And you frequently will see this kind of thing in these digital system designs where you have some control values and you feed them various places. And it doesn't, when we want to branch, it doesn't mean that the opcode is not also going to the ALU. The ALU may look at it and say, I don't know what to do, and output 0. Or it may output garbage. But the idea is that we only activate the parts of the circuits that we actually care about. So even though the opcode is going to the branch logic and the ALU, the branch logic won't activate unless it sees B or Z. the ALU generally won't activate unless it sees an opcode that it recognizes. So even though these signals are going to them, they'll just basically ignore what's going on unless it's something that they need to specifically pay attention to. So keep that in mind, because it's going to get more and more complicated as we go through our designs today. So we have an updated processor now, and this is something that you probably take for granted, but before we had this branching capability, if we wanted to do a large computation, we had to write a large program. And if we wanted to do a small computation, we could write a small program. But we really couldn't reuse parts of our program to do multiple different computations. But now we can, because we can loop. So now we can have a small program that does a large amount of processing just by putting loops into our programs. Okay? And it doesn't seem like a big deal, but it really is a big deal. We need to have this capability on the processor to be able to do, our general purpose computations. When I was in CS20, which we don't offer anymore, it's been decomposed into CS21, 24, and 38, the professor said in one class, all interesting programs have loops. So now we can run interesting programs on our processor. So with this instruction and this new capability, we should be able to encode our program. But you can see now that it's going to be a little bit more complicated. We have more variables, which isn't too scary. We already have an idea about how to handle that. We clearly have some constants that we're going to have to think about. And we have this new thing that we have flow control. We have while statement. We have to figure out, well, where's the start of the while? Where's the end of the while? We have this if statement as well. And so clearly it's going to become a little bit more complicated to do this planning. So writing the program is going to follow the basic process we had before, but we're going to have a few more steps that we have to go through. So we have our inputs and outputs. This is easy. We have A and B and P. Those are our inputs and outputs. We have to think about constants. We have this while A is not 0. Well, we can probably figure out something with our BRZ instruction because we know it kind of implicitly knows about 0, so maybe we can avoid encoding 0 in our program. So we can think about some of these things. So we have to start decomposing this into our processor instructions. And like I say here, we will probably need temporary values. If I say if A and 1 is equal to 1, or A and 1 equal to 0, then I need to compute A and 1 before I do anything based on that value. So I may need to store that into a temporary memory location just to do that computation. Okay? So let me see, in various addresses for branching. We use the same strategy that we use in algebra. If we don't know something, we put a letter in its place, and then we fill in the value of the letter later. Mike and I were just talking about this 2 days ago, that really all you need to know to be a good programmer is algebra, because there's a lot of situations where you have values that you don't know when you're writing your program, and you just put a name in instead, and then later on it gets replaced with values, or you associate values with those names. So like it says here, you write the code you do understand. You always have this approach. It's a progressive development process when you're writing a program. So you write the code you know, and then that gives you information that you can use for the parts that you don't know. So this is our code. These are our operations. First step is going to be to set P equal to 0. Now we'd like to not encode 0 into our value. I mean, we actually could. We could say P is going to be here, but we're going to initialize it to 0. You'll see that, since we can store constants anyway. But let's say that we're going to do it with our instructions. What options do we have for setting P to 0? Yeah. Yeah, we could subtract P from itself. That means whatever value was in P before, we subtract that from it, and now it's 0. What's another way we could do it? Yeah, XOR. Yeah, that's a good one as well. Again, why would you choose one or the other? Well, it depends on if you have a modern superscalar architecture where there's multiple ALUs, and if I can keep the ALUs free for some operations, then I can use them in parallel and so forth. That gets back to the whole pipelining concept. Logic tends to be simpler and tends to be done in parallel to arithmetic, so you frequently see code that does the XOR option. Like it says here, subtract P from itself or XOR P with itself. And because of little considerations like that, you frequently see the XOR option because it either is going to be faster or it allows the ALUs to be available for other operations. Okay? So just be aware of that. You're going to probably see that in code that's generated by compilers that you will be looking at. Okay, so that's the first step. We know we can go ahead and clear P that way. So we have XOR P, and store it into P. That was easy. Okay. Now we also know that as long as this expression A is not 0 is true, then we need to be able to go back to the top of our loop. But we don't know what that address is yet. We could probably actually guess the address since it's right at the beginning. But we need to go ahead and add a name, or in this context it's called a label, to our code, and that label represents an address in our program, so that we can jump back to that address at the end of our loop. Okay, and yeah, like I say here, we already do this with our variables. So we already know P is probably going to be address, what, the topmost address in our memory. We had this small convention that the arguments would be at the top of the memory, or the lowest addresses, and the result would be at the bottom of memory, or at the highest addresses. So we'll go ahead and we could presume that P will probably be 7, but we're not going to put it in there yet because it's easier to say P than it is 7. Okay, so we have this. And we don't know what's going to go inside the loop, but we will need to exit it. What's going to be our test for when we exit the loop? This is really easy, right? Because, yeah, we have a BRZ instruction, and we stay inside the loop until A is 0. So branch is 0, out of the loop. So we can go ahead and do something like that. And again, we don't know exactly where we're jumping to yet. But we'll put a label in there. We'll call it done, just because it's simple and we're simple. So we say BRZ A done, and that'll take us out of the loop. Okay? And of course, after that, we also need to be able to jump back to the beginning. So it looks like we'll handle that later. The next thing we're going to translate is this A ampersand 1 thing. Now, what are the possible values of A ampersand 1? It's a really obvious question, right? Yeah, it could be 0 or it can be 1. And you'll notice that the way that this if statement is implemented, we have if A and 1 is 1, then we do the body of the if statement. Well, you can also think about that in the inverse. If A and 1 is 0, the only other possible value for that expression, then we want to jump over the body of the if statement. So we can implement this easily as well with our branch if 0 instruction. So and A1 temp, and that temp value can only take on the values 0 and 1. And then we'll use a branch instruction to jump over the body of the if statement. And again, we'll just add a label skip. We don't know exactly what the address will be yet, but we're going to skip over the body of the instruction. Okay? So, from the looks at it, do you think that the rest of this is pretty straightforward to implement? There's not really anything else that's complicated here, save perhaps getting back to the top of the loop when we finish the current iteration. But we know that there's an add instruction, P equals P plus B, add P, comma, B, comma, P. And we can shift A right 1 bit, we can shift B left 1 bit, that's no problem at all. So we can just throw those things in there, sure AA, shoal BB. And then we need some kind of unconditional branch. So what we'll do is we'll just say branch is 0, 0. That will always branch. So we can do something like that. And so you can see that we clearly have a few constants now that we'll have to store and we'll have to utilize in our program. Right? So this is what we're going to do for now. Are there any questions? Okay. Yeah, so we can see that we manually implemented our while loop. Basically, we test the inverse of our condition to jump out of it. Now, is this the best way to do it? Not really. It turns out that there's better ways of translating while loops, which we'll talk about in probably next week. But anyway, we test the condition at the start, because that's how while loops, that's the semantics of while loops. And we test the condition at the start. We jump out if the condition is no longer true, or if it was never true, we skip over the loop entirely. And at the end, we do an unconditional jump back to the top. Okay, so that's our while loop. Same thing with our if statement. We test the inverse of the condition and skip over the body of the if statement if the inverse of the condition is true. Okay. Yeah. All right, so this is our assembly code, and we can go ahead, now that we know all the values that we need, we can assign locations to them all. We already settled on A and B being addresses 0 and 1, because that was our little convention that we decided to follow. And address 7 is going to be where the output comes out. And we needed a temporary location for computing A and 1. We needed a constant 1, and we need a constant 0. So these are the things that we could do. And of course, you could look at this and say, well, we're already initializing P to be 0. We could also initialize slot 4 to be 0 by doing XOR of slot 4 with itself. Certainly we could. In fact, we could compute a value for slot 3 as well. We could XOR slot 3 with itself and then add 1 to it. But we're going to keep our code simple. We're just going to have those constants in there. Now, once we have this, we can start updating our code, and already you can see it instantly becomes less readable. So we go in and say XOR 111, 111, 111, and we all know, well, 111 is 7, and that's where P was, so we're okay with that. But you can see that already it's starting to lose its comprehensibility for a human being. And then we have while and skip and done, and you can see that I've labeled each instruction with its address in the instruction memory, so we always at least at this level, start at address 0. So the first instruction is at address 0 and so forth. So you can see that the while's address will be 1, the skip address will be 5, and the done address will be 8. And wherever we have done, we can replace it with 8. Wherever we have skip, we can replace it with 5. And wherever we have while, we can replace it with 1. So we do that. And it becomes even less comprehensible. Okay. Now it's interesting because just as an aside, even assemblers have to make multiple passes over the code to do this kind of thing. When you write assembly language, the assembler will actually make a few passes to figure out these kinds of things. Like it will lay out all the instructions in memory, how much space does each instruction take, now I know my label addresses, and then it'll go through and plug those things in, and you can see that it would make multiple passes just to generate machine code even from that very sort of small step from assembly language down into machine code. It's kind of interesting that even at that step, sometimes multiple passes are necessary. Okay, so we're going to encode each instruction into machine code. All we're really doing now is plugging in opcodes. So XOR is 1010, BRZ is 0111. So we go in and plug each one of those values in for the corresponding opcode. Yay, look at that. So comprehensible now. This implements multiply for us, driving our little processor. Okay. Now, you can see that I have a lot of grayed out bits. The grayed out bits are actually bits that we don't care what their value is because they are ignored by our little processor assembly. Those bits really are irrelevant. XOR, we don't care what the branch address is. XOR doesn't use the branch address, so nothing will actually look at that value and use it for anything, and so forth. Same thing with branch of 0. You can see that we don't care about the second operand and the result. So this is a pretty inefficient encoding of our instructions. But the nice thing is that our instruction decode step is basically non-existent. I mentioned briefly last time when we were talking about what it means to pipeline execution of instructions. And part of that is decoding instructions, figuring out what the various bits in the instructions correspond to inside the processor. We don't really have that step because our bits in our instruction drive the machinery very directly. So we have a lot of waste at this level. But that's fine. But what you do notice is that on processor architectures, particularly CISC architectures, where we can have instructions of many different sizes and so forth, the instruction encoding is tuned so that it will take as few bits as possible to encode everything that you need the instructions to do. And then obviously the complexity of the processor's instruction decode logic becomes that much more complicated. Now you have to start interpreting things to make sure that you activate and deactivate the appropriate components of the processor. Okay? Are there any questions about this? Okay. Yeah, for example, I wish I had it. It would be really cool to just show you this right now, but I don't have it in the slides. If you happen to look up the processor die for any of the modern Intel processors that we program, you'll see, like, especially if you can find one that's labeled, you'll see like a big chunk of logic that's like instruction decode. And that's entirely doing this whole thing of translating the bits of the instructions into what components of the processor should be utilized. Now, another thing you'll notice, we have this kind of weird layout that you're probably not used to. You know, the way, like, I have a MacBook here, and I know that I have a processor in there, and then I have a big giant memory. Well, big giant compared to what I started with, at least, when I was a youngster. There's like 8 gigs of RAM in there, and then there's a disk and so forth. It's not really laid out this way, because I know my programs are loaded into the same memory that my data is in. And that's not the same way that this is implemented here. I have instructions in one memory, and I have data in another memory, and you can see that the only way to write to memory is involving the data memories. It doesn't involve the instruction memory at all. The instruction memory is read-only. Yeah, and I have these 2 data memories that are mirror copies. That's just a simplifying thing, actually. So it turns out that there's a number of different ways that you can construct computers and how you can lay out the memories in these computers and how the memories are utilized. The one that we've been looking at just now is called the Harvard architecture. Because this is the way, I think I actually have this. I should actually tell you why it's called the Harvard architecture first. But it's named after the first computer that was designed that actually followed this memory architecture. The Harvard Mark I, which used relays for all its computations. I can't even imagine what it would have been like to be in that room with that giant computer, because it really was a large computer, and it could do very little. But what it could do, it was perfectly capable at doing. And of course, all the relays would be clack, clack, clacking away as the machine was doing its computations. Very slow, much slower turning on relays and turning them off than it is turning on and off semiconductor gate. Okay? But anyway, like it says here, the instruction memory and the data memory are separate from each other. They may have different word sizes or how many bits are in the values that we store. As they are in our case, we have an 8-bit data memory. And I can't even remember how many bits. How many bits were in our instructions? 1, 2, 3, so 9, 10, 11, 12, 13, 14, 18 bits? Something like that? There's something wild. It's something that we're not really used to. But anyway, so we had these separate memories, and they have different widths, bit widths, and the data memory is the only one that's writable, and the data memory is really the only one that's fed into the ALU. So it's not possible to treat instructions as data, which means that we have to explicitly load our constants into memory if we're going to manipulate with them. Okay? So it's kind of an interesting thing. You have to go through a lot more hoops because of the way the architecture is defined. Now, does anybody remember where the term bug came from? You may know this little anecdotal piece of history. Yes? Almost correct. Yeah, it actually got wedged into the context of a relay. So the relay could no longer open and close. And that was actually the Harvard Mark II. The Harvard Mark II was the one that got beset on by moths, or I should say a moth. It's actually, I believe the moth is displayed in the Smithsonian. So it has to be the most famous moth ever. But yeah, it's kind of curious that. But anyway, so the Harvard Mark I and Mark II computers have a storied past and have had a big impact on computer architecture. Now, the architecture that we're all used to also has a name. It's called the von Neumann architecture. And in the von Neumann architecture, instructions and data are kept in the same memory. So that makes it much easier to load different programs into the memory because you're treating it as data when you're loading it, and then I want to switch over to treating them as instructions. So that's the obvious benefit. But there's also obvious drawbacks when you have a von Neumann architecture. What are some obvious drawbacks of using a von Neumann architecture versus a Harvard architecture? Yes? Yeah, I can accidentally or sometimes intentionally modify the code. Which is interesting because, again, this used to be done all the time by hackers, and I mean hackers in the good sense, the old sense that I wish would be resurrected and everybody would use it, but I think that ship has sailed. As much as Mike doesn't like that, it's unfortunately reality. that people would write programs that would modify themselves. And you could create some incredibly tight, clean programs. I shouldn't say clean because they're probably the dirtiest thing you could do. But you can modify instructions that you'd already executed and then jump back and execute the code again, and it would be slightly different. Or you could use instructions as data. And there's some really great stories on the internet of programs that were written that way and to great effect. So that's kind of a fun thing. So it used to be done intentionally for fun and profit, but now it's done intentionally for not so good reasons, nefarious reasons. Like I'd like to be able to get a program to do something other than what it was implemented to do. And we'll talk about that when we get to week 4 and we start talking about higher level languages and some of the constraints that higher level languages would like to apply. So that's one obvious issue. What's another one? There's actually a performance-related issue that you could come up with the von Neumann architecture versus the Harvard architecture. I'm sorry? You're on the right track. It has to do with the buses. It's the fact that you use the word buses instead of just bus. Right? If I have instruction memory and data memory separate, then I can have separate dedicated buses to those things, and the processor can access those things concurrently at the same time. I don't have to wait for the instruction to be executed before I go and start loading the next instruction. I can start loading it right away. So I can parallelize those operations. On the von Neumann architecture, if I'm accessing data, I can't access instructions. If I'm accessing instructions, I can't access data because I have one bus, and it can become a performance bottleneck. Generally, we have approaches that allow us to avoid this stuff. Okay, but these are some of them. So yeah, programs can easily corrupt their own code. Then we have this performance issue that the processor can only load instructions and data across one bus instead of having 2 separate buses, which would make it better and faster. And so what modern processors frequently do is they blend these architectures. Just like I was saying that RISC and CISC are kind of no longer ends of the spectrum, processors blend them because there's benefits of both. Same thing with the Harvard and the von Neumann architectures. Internally, on the processor die itself, again, if you pull up a processor die diagram that's labeled and everything, you'll see a big chunk of the processor that is instruction memory. And it is used only for instruction, so it's accessed only in very specific ways. And then you have another section which is data memory. These are caches of the main memory. We'll talk about why we have that in the future as well. But the data memory is separate and it's used in different ways. So internally, the processor is kind of designed like a Harvard architecture system. But externally, it still interacts with the system's main memory as if it was a von Neumann architecture system. Okay? So you see that you get a blending, and the processor is able to access the instruction memory in optimized ways because it only has to access instruction memory in a few ways. It kind of doesn't expect that instructions will be changed, which is a good assumption. Most programs no longer change their own instructions. Okay? Any questions about that? Okay, so that's the idea behind these various memory architectures. Now there are other programs, like we have loops, and we're like, oh, we can write programs that have loops in them now. But there's other things that we can't do because our addresses are hard-coded into our instructions. So here's an example function. I want to write a function that takes 2 vectors as arguments, sums their elements into a third vector. I can't do this on my current processor because I only have direct memory access where I specify the address in the instruction. I don't have any kind of indirect memory access. Here's the code that you might write. If you're not already familiar with this, you probably are already starting to sense that there's a similarity between pointers and arrays because I'm passing in pointers to ints and I'm using them as arrays. We'll talk about that relationship in the future. I think probably next time. But anyway, this code is independent of the location of the data that it's supposed to be processing, which is nice. We already have a loop, so we can process arbitrary sized vectors just by specifying different lengths. I don't have to, if I have a 20 element vector, I don't have to have 20 steps in my program. I can just have one step that I iterate 20 times. But I'm not able to implement this because I don't have indirect memory access on my processor yet. So if we look at the way that we've done this, we have these data memories, and you'll see that we have A and B fed into our data memories, and we don't really have a way of feeding something that's not a constant encoded in an instruction into our data memories. So we need to somehow change this logic. And like I was saying before, in general, if you're designing a processor, you want to design the processor to do all the things that you want from the beginning so that you can have a nice, elegant, clean architecture. But since we're refining and developing this whole model, we're going to bolt something else on here. We're going to add a new way of this thing working, but we're going to try to attach it to what we already have. Okay, so we need to update the hardware to support indirect memory access. We have another problem, though. Because right now we only have 8 addressable memory locations. And that's not very much memory. I can't do a whole lot with that. Okay? If you're doing 156 and you're doing the Netflix challenge, there's no way you could do it on this processor. We don't have enough memory for it. So we need to have some much larger memory than that. But we're going to run into a design issue if we start increasing the memory size. So let's say, just as a thought experiment, we decided to increase our memory banks, A and B memory banks, to be 4 gigs instead of 8 bytes. Kind of a big jump, right? So what will happen to our system if we decide to increase our memory banks to 4 gigs instead of 8 bytes? Yeah, it increases by a lot. Everybody see that? So if I have 4 gigs of memory, so I have 4 billion, give or take, memory locations, then I need 32 bits to address those memory locations. And right now I'm hard coding my memory locations into my instructions. So I can sit down and do some math. Right now we have 3 times that addresses appear in our instruction. So 32 plus 32 plus 32 plus a write bit, our branch address, which we're going to assume that our instruction memory stays, small, which I don't know why we would do that. But anyway, we'll keep the instruction memory small. But you can see already we're getting up to like 100 bits per instruction, which is ridiculous. We don't want to do that. So we need to come up with another design. And this is the design that most systems actually use. So we have a small memory here, which we will now start calling a register file. And if you've ever heard the term registers, then this is where that comes from. It comes from locations in the register file, which the processor is able to operate on, perform arithmetic on, and it can operate on them very rapidly because the register file is stored on the processor itself. Okay? And like I said, you have a small number of registers, 8 or 64. It turns out, you know how we talk about CISC architectures versus RISC architectures? CISC, very complex. They have a whole bunch of logic devoted to processing instructions, which means there's not a lot of space left over for registers. And so they tend to have a relatively small number of registers. Did I get that right? CISC architecture. Then RISC architecture has simple logic. And so there's a lot of space that it can devote to registers. So RISC architectures tend to have many, many registers. So that's kind of a trade-off, another trade-off that you see between RISC and CISC. RISC will have tons of registers. CISC tends to have very few registers. And you'll see why as we get into this. It turns out not to be too terribly limiting. So yeah, the instructions only encode register addresses, so the instructions get to stay small. If we keep ourselves to only 8 registers, then our A, B, and res, for result, that's what res stands for, A, B, and res will all just take 3 bits. And so our instructions won't grow that substantially. The ALU only operates on register values, which means now we need to have a way of pulling values from the main memory into a register, and we need a way of storing values from registers back into main memory. So we start introducing new instructions. As you can see here, load store logic. we'll have a special opcode that is, I want to load a value from main memory into a register. And I want to store a value from a register back into main memory. And the address will come from another register. Okay, so we'll have load, source dest, and the way that this works is we're loading a value from main memory, so the address will be in source. That'll say where we're pulling the value from, and the result that we load from main memory will go into dest, just like I have here. Dest equals memory source. And again, you can see I have all these red lines. The red lines are the ones that we care about. All the other lines, it doesn't mean that there's no signals going out on those buses. It's just other things are ignoring them. So we send the opcode, the load opcode down, and it hits the branch logic. And the branch logic is like, well, it's not BRZ, so I don't care. Shut up, go away. It hits the load store logic, and the load store logic is like, load. I was built for load. Here I go. And the ALU sees load, and it's like, I don't know, and it just shuts up. Okay? So these values are still going places. You can see that A goes into the thing. So source is going to be A. So that goes in, and we send that value down to the read address on the main memory. It also goes to the ALU, but the ALU doesn't represent or recognize the opcode, so it's like, whatever, I don't care. Goes down to the read address, and the value of that memory cell comes out of the main memory on D out, and we also activate our multiplexer so that that value goes back into the register file. So we're pulling a value out of main memory and storing it into the register file. The specific register being specified by dest or res. And so that is set on the right address. The right bit is 1. We store our value. Okay, questions? A little bit complicated. Just follow the lines, especially the red ones, and you'll be okay. Store, same thing. We have a value in source, and we want to write it to the memory location in dest. So again, if we were saying what this means in a higher level language, memory dest equals source. And so again, we activate the load store logic. The load store logic also recognizes store. And you can see what it does. It activates the right bit now on the main memory because I want to store something. The A value from source is going to go to the ALU. The ALU doesn't care. It goes to the branch logic. The branch logic doesn't care because it doesn't recognize the opcode. It also goes down to DIN, or the data in value that's going to be written into the main memory. The B value also comes down. It goes to the ALU. The ALU doesn't care. It also goes to the right address. We've set the right bit, so D out is ignored and blah, blah, blah. The value is from A is stored at the address specified by B. Okay? Does that make sense? This is basically what's going on here. Yeah, and as you could probably guess, if I haven't already said it, this is called a load store architecture. Because the ALU only operates on registers. You can only add 2 registers together. You can't say, I want to add the value at this memory location to this register. You can't retrieve it that way. Or you can't say, I want to add this constant to a register. I want to add this constant to a memory location. You're not allowed to do those things. You're only allowed to operate on registers. And so if you want to manipulate data values, you have to read them from memory using a load instruction, and you have to write it back to memory using a store. Okay. And the benefits are the same as always. This is a very simple approach. So the instructions are simple, and you can pipeline them. You can make them all execute very quickly. You can optimize them as much as possible to make them execute quickly. And so you tend to see this on RISC architectures, not on CISC. Okay. The drawbacks are also obvious. If I have to do a lot of memory manipulation, then I have all these load instructions and store instructions because I can't manipulate them directly. I have to load them into registers before I can manipulate them. So I end up with a lot of loads and a lot of stores in this approach. Okay? So if I did want to implement my vector add, I have this simple thing. Oh, I'll just sum AI and BI into RI. It's so simple, right? But the problem is that if you're going to implement this, then you have a whole bunch of instructions. You have to figure out what's the address in memory that I need to operate on. So like I have here, A is the starting address of the array. So I have to add I to it to get the address that I want to manipulate. So A, I, and adder are all registers now. and then I load the value in main memory at that address specified in adder into a register AI, so I retrieve it. Then I do the same thing for B. I retrieve that value B sub I into BI. And now I can add them together into another register RI, and then I need to figure out where to store that and write it back to main memory. Big pain in the butt. Now this is one way to do it, like I have here. One implementation of RI equals AI plus BI. If I were going to implement this myself, I would probably just keep incrementing A and B, and R, of course, to go to the next element in the array. But unfortunately, that doesn't simplify your life at all. You still end up with the same number of instructions. Okay? So, kind of annoying. Kind of really frustrating. Yeah, like I say here, hopefully the processor is good at this stuff so that we can have these programs that do simple things like add two vectors together, and it's able to do it fast, even though we have to do a whole bunch of extra work that's imposed by the architecture that the processor implements. Okay? So there is another alternative to load store, which is what we will be using all term. And it tends to be what CISC processors offer. It's to have a whole bunch of different operand types besides just registers. So now I can have instructions that encode constants. So I don't have to actually have a register that I set to a constant before I run my program. Or I have an operand that is a memory location. Or a register that's used for a memory location, and I add an offset to it. There's a whole bunch of things you can do. Okay? So a constant, a register, so I want to add 14 into R1 and store, actually I should say 14 plus R1 becomes R2. A direct address, so I want to retrieve the value at address 150. I want to add 14 to it and then store that value into R7. You can see that I have three different operand types here. An indirect address, 150 plus R5. I could use this for my array indexing. So that now, R5, actually I should say the 150 would be the start of the array, and R5 could be my index. And I could just keep updating R5 and reuse the same instruction. So I could do something like that. So you can see that having a variety of operand types, some of which include direct and indirect memory access, can be very powerful. It can greatly shorten your program, except, you think, okay, I have fewer instructions, but now each instruction has to get more complicated to encode all these different kinds of operands. So the instruction gets larger. And so it's kind of interesting, where is the trade-off? Like, is it better to do RISC with small, simple instructions where I need a lot of them, or a few large instructions where I need fewer instructions, but they take more data to encode? Okay? It's an interesting area to sort of explore. So if I'm going to do this, I need new logic. No longer can I just have a bus going straight down into my ALU from my register, because values can now come from various places. What tool do I now need to plug in between my register file and my ALU? We have them a few places up here. We have one feeding the program counter. We have one feeding the values going into the register file. I need to start dropping multiplexers into various places so that I can say, yeah, for this instruction I want to take a constant. For this other instruction I want to take a register. And for this other instruction I want to take something else. Maybe sum some things together. Okay? And so we can do that, but we also need to increase the sophistication of our encoding so that we can say what things are. And so, like I say here, you can see that CISC processors, this is part of what makes instruction decode so complicated, in that we need to figure out these various instruction operand types and handle them correctly. Okay? And then also, like I have here, we may need to do arithmetic if we're doing indirect addressing, where I have a base address plus a register value, or if you're IA32, you can do a base address plus one register plus another register. You can actually do some very sophisticated things. You can even throw multiplication in there as well. So here's some example logic. We're just going to upgrade one operand. Because if it gets this complicated with one operand, you can imagine how much more complicated it would be with two operands that support various operand types. Okay? Well, we have more wires now. We have more things that we need to do in various places. But this is a nice, simple illustration. Like I say here, operand A supports 3 operand types in this simple design. The way that we tell which one we're doing is with that MA value in the instruction memory. That's the mode or the operand type of A. So we can take a constant, which is encoded in CA, and you'll notice that the constant feeds to various places. I'll have more red lines, so it's showing you where it will go. So don't worry about it right yet. A register, which is still encoded in A, like we had before, and a memory access, which is going to be indirect, a constant plus a register value. And that will use both A and CA. So you can see that CA, for example, feeds down to this little adder thing, and it also feeds into our multiplexer for the ALU. Okay. And then operand mode MA, which I already talked about, is what controls these various components. And like I was saying, we're only upgrading one because to do more would be really complicated. But there's a lot of other things that we could do as well. Like right now, we only have A being the awesome multiple operand type argument. We'd also want B to be awesome, and we'd also want the output of the ALU to be awesome. So when you start looking at that, you say, oh, then I could actually try to factor out some of this logic and try to reuse that component, or maybe stamp out multiple components and then route things through them in various ways. Obviously, that starts to get into processor design, and that's beyond the scope of CS24. But it just illustrates what's going on. Okay, so constant operand. MA is set to say, I want the constant to feed into the ALU. And so CA comes down, and it goes into the main memory, but the load store logic isn't going to activate, so the constant is ignored. The constant also goes into this multiplexer feeding the ALU, and the MA value says, take that constant and use it as your first operand. And so the register bank A is completely ignored. Okay? So either CA specifies a constant value, MA feeds CA through to the ALU, and the memory and the register are both completely unused. Okay, does that make sense? So that's if we had a constant argument. If we have a register operand, again, MA will be set to use the register file instead of CA. So again, CA may have a value on it, or it may not, we don't know. But that comes down into the multiplexer, and the multiplexer ignores it because MA is not set to use it. So the register value A comes down, and that feeds into the ALU, and that is what is used for the computation. Okay? Excuse me. So A specifies the register address, the register file outputs the specified register value, and the MA feeds the register to the ALU. Simple, simple. Okay. The last one is a little bit complicated. Indirect memory access. So now MA is going to say, this is an indirect memory access. And so we need to go ahead and figure out all of this stuff. Let me see. Yeah. So MA goes down. Yeah, so it says I'm going to take the third option. CA goes and feeds an address into the adder. So why do we have an adder down here for the read address? It's so we can do that whole constant plus register value thing. I need to add the two together to get the address I'm actually accessing. So I have to actually do arithmetic down here. So you can see that figuring out the address to access actually takes some logic as well. And it's funny because on IA32 you can actually take advantage of that. And so I think it's in the second assignment. We actually show you how you can do some arithmetic with the address. I'm trying to think. I'm losing my train of thought. The address computation logic on the processor. You can actually use that to do basic arithmetic really quickly and keep ALUs free. You frequently see optimizing compilers do that as well. But we can take advantage of that little computation down here. So we feed the constant and the register value into the adder. That becomes the read address. And the D-out value is now selected by the multiplexer. That goes into the ALU for the computation. Okay. And I think I have it here. Oh, yeah, I don't have it here. So the value of A is ignored by the ALU because the multiplexer doesn't select it. And the constant is also ignored because the multiplexer doesn't select it. Okay? So that gives you a sense of how we can implement this rich operand type thing. And it's CISC, and IA32 is CISC, so you're going to have a lot of rich operand type. And as you write your assembly code throughout the term, and you do things like access elements of structs, access elements of arrays, I want you to think about the fact that you're using this kind of logic on the processor and how much simpler it makes your life. How many fewer instructions you have to write because the processor is doing all of this kind of complicated stuff behind the scenes. It's actually offering quite a sophisticated set of abstractions for you. Okay, let's wrap up. We just have a few more slides to go through. We added branching. So now we can actually reuse instructions for larger computations instead of having to add more instructions for larger computations. That's a big step forward. So the work is now proportional to the input values as opposed to the number of instructions we have. And we also had various memory architecture details. We had the load store architecture. I don't know if so we had load store and we had rich operand types. We also had Harvard versus von Neumann. Okay, so we talked about those things. You can read more of those details if you want later. Now, if we were to take this processor and make it any more sophisticated, it would be a waste of our time because we're now starting to get to the level of sophistication of the actual Intel IA32 processor ISA. So what we're going to do next time is we're going to start talking about how IA32 works, and we're going to start talking about, well, how do we implement even more sophisticated abstractions, like subroutines, which you probably never thought of a subroutine as being another abstraction, but we still have a limitation with our processor that we can't write a piece of code and then reuse it in different parts of our program. That's a limitation we still have with our processor. So we'll start exploring how do we implement this notion of having a subroutine. Okay? So, and that will basically be what we talk about next time. Any questions? Okay, see you on Monday.